Hello everyone, welcome to a new video on group theory. I realized after I posted my previous video that there are a few more things that I need to explain before we start solving problems. Okay, so let's dive into the math immediately. The first thing I wanna talk to you about it is the notation. Remember that in my previous video I was saying that we have a group G equipped with an operation that I used to call star, and I was operating elements by writing A star B. Okay, so I'm gonna abandon this notation and I'm gonna start writing A star B as AB. Okay, this is a little confusing because seems that I'm multiplying A times B. And also sometimes, I don't know why, and it makes it very confusing, we talk about this operation as multiplication when it's actually not necessarily multiplication. So please, when you see AB, do not assume, since we are used to, since we come from multiplying numbers, that A and B are numbers and they're multiplied together. Okay, so remember that A can be a matrix and B also can be a matrix, and we are adding or multiplying, we do not know. So from now on, this AB means the element of the group A operated with the element B of the group. Okay, let's move to the next thing. I want to talk to you about the cancellation law. So, cancellation law. Okay. In a group, the left and right cancellation laws hold. Okay. So remember, the left and the right cancellation laws hold, which means that if A, B, and C are elements of the group, remember, AB means A operated with B is equal A operated with C, implies that B is equal C. And also, BA equal CA also implies that B equals C. Sorry, that B is equal to C. Okay. I believe that this needs a proof, so we clarify a few points. Okay, let's give a proof. Okay, because I want to give the proof because this seems, again, since we are used to deal with equations, that is mostly real numbers, even complex numbers, that this always is a straightforward properties that comes from multiplication, but in this case is not. Okay, and here is the proof. So let's have a group G. Let's G be a group. Okay, and let the elements A, B, C, and D be element of the group G. And assume that AB is equal AC. Okay, first remember, by the definition of the group, every element of the group has an inverse. Okay, so all these elements have inverse that are in the group. So let this guy be the inverse of A, such that A inverse operated with A, you know, that is equal to the identity E. All right, so let's multiply these two terms by the inverse of A in this way. A inverse times AB. I'm gonna say times AB, but you know that I do not mean necessarily multiplication. Okay, it's just to be a little faster without saying all the time operated. Okay, so and then let's operate a inverse with AC. Okay. Now remember that since G is a group, the associativity property is guaranteed. So with the associativity property means that we can move parentheses around. Okay, so this becomes A inverse A B is equal A inverse A C. Okay, I just move the parentheses around. This becomes, these two guys cancel out and becomes, these guys cancel out, become the identity E C. Okay, and you know that the identity times an element is the element itself, so we have that B equals C. Okay, and for the, and this we prove that the left cancellation law holds. For the right cancellation laws is the same exact thing, just multiply by A inverse on the right and you're gonna get the same result. So this not only proves that you can do this step, okay, but this needed to be done because it is not guaranteed. Remember that we're not multiplying real numbers. It is not guaranteed that if AB is equal to CA, this does not imply that B equals C. Okay, this is not working. Remember that these are elements, they're not numbers. If they were matrices, you already know that AB and BA is not necessarily the same. They're not necessarily the same. Okay, so we can only operate on equations involving elements of groups. You can always work on the left side or on the right side. Okay, you're not allowed to commute elements. So this, if I had to if I had to do the same thing to this equation, I would do A inverse AB is equal A inverse CA. Okay, and then this will become B equal A inverse CNA, and there's nothing else I can do over here. Okay, not, at least not by just shoveling things around. I cannot do it because this group, unless it's specified, I cannot assume that the elements, that I can commute the elements. Okay, so this is not, this does not imply that B equals C, or this does not imply this. Okay, this doesn't follow from this. However, so now this gave me the chance to talk about something else. What is an abelian group? We know that we already know what is a group. And let's state it again. Okay, a group is a set of elements equipped with an operation. And remember that to prove that this set is indeed a group, under that operation it needs to satisfy closure, associativity, it needs to have an identity, and every element needs to have an inverse. Okay, so this is a group. An abelian group satisfies one more property, which is commutativity. Okay, so in an abelian group, so if G, an abelian group G, okay, if A and B are in the group G, then we have AB equal BC for all excuse me, AB equal BA for all A and B in the group. Okay, for all the elements can be commuted. Okay, so to be clear, to make a little example, we saw before I didn't allow you to do, if you have A and B equal BC, let's do it the way I did it before, B equals CA. Okay, I did not allow you to imply that B equals C. Okay, but if now I say that A, B, and C are element, A, B, and C are element of G, and G that is abelian, then yes, this statement is true, because AB equals CA implies that AB equal AC. Okay, because all the elements of an abelian group can be commuted. So this, we have the commutative property CA equal AC. Okay, and now I can multiply, I can operate it by the inverse of A, and remember, I can shuffle things around. This and this are inverses of each other, so this is the identity, and follows that B equals C. Okay, so a group satisfies 4 properties. Let's write them down again. Closure, associativity, identity, inverses. And if G is abelian, so only for abelians, commutativity. Okay, if a group is commutative, then it's abelian. Okay, so remember that if a group is abelian, then it is specified. Okay, if it's not specified, then do not assume that is abelian, so do not assume commutativity, do not commute elements. Okay, you'll see in every problem, so in every proof, you'll be asked to in the statement you'll find, okay, let's G be an abelian group, or sometimes you'll find let A and B be element of a group such that AB equal BC, AB equal BA. Okay, so this is important. Do not ever assume commutativity unless it's specified before. Okay, and also every time that in a proof you have to prove that a group is abelian, you always want to have this final result, AB equal BA. Okay, or if you have to assume, if you assume that the group is abelian, so it has other properties, then start this way. This, when they tell you a group is abelian, that what you can assume. And obviously out of being abelian, that's the only thing you can assume, but you are allowed to assume this. Okay, now I owe you another proof. This is another important property of the groups that you're going to use a lot, so I'm going to state it and I'm going to prove it. Okay, so it's called the socks shoes properties. Socks shoes property. Okay, it says that in a group we have the A B inverse is equal to B inverse A inverse. Okay, so not the other way around. No A inverse B inverse. Okay, um, remember I said in a group, not in an abelian group. So if this was abelian, this would, you could commute this to, but I didn't specify it, so might be abelian or not, we cannot assume it. So in a group, this holds. Okay, and let's give a proof. Okay, let's G a group with A and B in it. Okay, so let me make a little box over here. Remember that we said when we were defining the group that the every element has an inverse, and the inverse is the element. If A is in the group, then A inverse is the element for which A inverse is equal the identity, but is also equal to A inverse A. Okay, so the identity, the inverses are commutative. So A inverse is equal to A inverse A. Okay, this followed by the definition of the group. Okay, so we just talked about abelian groups. Okay, this is not a property of abelian groups. This is a property of all the groups. In each group, the elements can commute with their own unique inverse, and also with the identity. Remember that also AE equal EA equal A. Okay, so these two elements are commutative in every group. In an abelian group instead, they're all commutative. Okay, so keep this in mind, and let's analyze this guy. Okay, so look at this. AB inverse times AB, by the definition of inverse, is equal to AB inverse, right? Now let's pick one and let's make this. Okay, these are inverses of each other, so this generates the identity. Okay, so let's cross them here, and we have the identity equal AB inverse. Okay, so let's multiply the identity. Again, I'm sorry, I'm using multiply, but I mean operate. Okay, we are allowed to say multiply, but remember that I'm not multiplying numbers, I am operating elements. Okay, so let's do it here. Okay, we have A inverse on the left. Remember that you can just operate both on the left or both on the right. So we have A inverse is equal to A inverse AB inverse. Okay, remember that by the definition of groups we have associative properties, so I can move this parenthesis here, or I can make it this way, and these two guys cancel out. Okay, now let me multiply by B inverse, and I multiply B inverse on the left side, so here and here, and let me rewrite it. I have B inverse A inverse is equal to B inverse B AB inverse. Okay, these two guys cancel out because they're inverses of each other, and this implies that B inverse A inverse is equal to AB inverse. and we have a result, and this is proven. Okay, so remember this called the socks-shoes property. Is going to be very useful in the future. So I'll see you in the next videos when we're going to be starting to do some problems. Thank you for watching.